Welcome to the Simplify 3D Machining with GibbsCAM webinar. We're going to get started. I'm Tony Ledbetter and I will be your presenter for today. GibbsCAM Advanced 3D Machining provides extremely efficient gouge-free toolpaths on solid or surface models with an interface that is both easy to learn and use. Unlike competitive products, constraint surfaces do not have to be selected, as all unselected areas of the solid model are automatically treated as constraints. Likewise, rarely is geometry ever needed to constrain toolpaths, as advanced 3D machining offers 6 different boundary types combined with 3 different boundary styles. GibbsCAM Advanced 3D Machining consists of 4 major process groups: Advanced 3D Machining, Surface Machining, Plunge Roughing, and Rotary Roughing. The first thing I want to show you is how to actually create a 3D machining toolpath in GibbsCAM from scratch. So what I am going to do is go to one of our tool libraries. We have the GAR, the Harvey, and Helical tool libraries are all included with GibbsCAM. I'm going to go to the Helical library. Now, I've already entered in some of the parameters for the types of tools I would like to be working with. And this one with 2 inches of flute length looks good to me. So I'm just going to click on the ID number, and you'll notice that it opens up a web page at Helical telling me everything I need to know about that tool. I can also go there and get the speeds and feeds recommended. And once I'm done, just go right back to GibbsCAM. And to enter this tool into GibbsCAM, you simply hit the import button. By the way, you can import as many tools out of that list at one time as you would like. Once I'm done with that, I'll close the tool library. And to do machining for 3D parts is just like any other machining process in Gibbs. You simply drag a tool to an open process area. It opens up only the applicable processes. In this case, I'm going to select Advanced 3D, and we're going to do pocketing. Typically, you only need to enter a few values, like your clearance values, and perhaps alt-click on the surface you want to machine down to. At that point, I can usually just hit Restore Defaults, and the system will select proper parameters for machining this part. Then I can hit the Do It button on that process, or this Do It button, or I can right mouse click anywhere on the screen and hit Do It. As I'm doing that, you'll notice I've got a process window showing me what the progress of this is, and it's already done at 100%. I'm going to switch here to OpSim to show you what this is doing. This is the process we just built. Now I want to show you a few different styles of the first type of process we're doing. There are 14 different processes in advanced 3D machining. There are 6 in surface machining, and then we've also got plunge roughing and rotary rough. So in pocketing, on this particular example, we are using the default of helical ramping. If I show you what the rendering is doing on that, just rewind here. You will notice that it makes helical moves into each area instead of plunging into the material. This is very handy, especially if the part's nested way down inside the vise and you don't want to, violate surrounding fixtures. So this is helical ramping. This next process is the exact same things, except under advanced settings, it's changed to profile ramping. And you will notice on this one, instead of it helixing down, you'll notice that it actually follows the shape of the toolpath as it moves in NZ. Sometimes that's more beneficial to use profile ramping. Okay. And then finally, Wanted to show you this. It's one little button in Gibbs called automatic core detection. When we do that, if you look at a top view, you will notice that the toolpath is not starting on top of the part at all, but it's actually entering outside the stock at typically a 45-degree angle, and then it radiuses into the cut. And this happens on every single cut. It's starting outside the material instead of above it. I'll show you the rendering for that. You'll notice it's never plunging on top of material at all. And that's all from that one simple switch, auto core detection. The next example I want to show you is called pocketing with core detection. For this example, I am using a slightly different part, and there's a reason for that. Pocketing with core detection is really designed for machining what I call thin wall parts. It's where you've got a very tall wall that's very thin, and if you were to try to rough that entire part all the way down and then finish it, your finish cut would typically either pull the wall into the part or push it away from the tool, and you just wouldn't get a good part at all. But what this does, actually, let me clarify that a little bit. What this does is it actually lets you do a primary Z step, and then you can do wall cleanup control and tell it how many different offsets you want to use. You've got a rough step over and a cleanup step over. So if you look at how it goes about doing this, you'll see that it actually cuts a rough cut, and then it cuts, you know what, let me switch to a front view for this. You'll notice it does one major rough cut, and then after it does that rough cut, it goes back and finishes down to that Z level, so that you're never gonna have to finish the part while it's not already being supported by the rest of the part in the stock below it. So anytime you're cutting thin wall parts, my recommendation is use pocketing with core detection. The next example we're going to use is adaptive pocketing. In adaptive pocketing, and in this case, we're going to go back to the part we were using previously. Adaptive pocketing looks very much like a volume mill toolpath, but it really isn't exactly the same. It does use circular motion to remove material, but I've actually got GibbsCAM set up here now for feed rate toolpath mode. So all of the cuts that you see in a magenta color are at a moderate feed rate, and all that you see in red are the rapid moves. So you'll notice everything is at the same feed rate. Let me show you this one real quick. So this is adaptive, and the toolpaths do look very similar. Let me slow it down just a little bit for you. The toolpaths do look very similar to a volume mill style path, but I want to show you there's two big differences. One of those, I'm going to switch now to the volume mill toolpath. And you'll notice with volume mill that the colors are constantly changing. Volume mill, when you create a volume mill roughing toolpath, you're using more of the flute first and then working your way back up the part. But as it goes into the material, it's always maintaining a constant chip load, which means your cutting tools are going to last longer, it's easier on your machine, and it improves cycle time. So let's look at this volume mill path now. You'll notice it also helixed to the very bottom first so it could use all the flute that it possibly could. And notice how this first depth of cut is much deeper than the first depth of cut we're using adaptive. And one of the real keys here is not only are we maintaining with volume area, maintaining a constant chip load, but also if you look at the operation manager and we let it calculate the cut times, you'll notice with adaptive pocketing, it took 4 minutes and 1 second. With the exact same tool and using volume mill at its recommended speeds and feeds, 3 minutes and 12 seconds. So adaptive pocketing is very similar to volume mill solids, but it's not exactly the same. In the next example, we're going to do lace cut. Lace cut is a type of finishing process that I would dare say is probably the most widely used finishing process. So if we look at this first one, we've got a lace cut, and on our boundary, we've got part bounding box, and the tool is going, the tip of the tool is going onto the boundary with our vertical and horizontal arcs in and out of the part, entry and exit styles. So this one is lace cut with boundary of on. And I'm going to show you this with tool sim instead of op sim. So you will notice that it's arcing down and then into the part, and between each cut you see these really nice B-spline moves. This next process, all we've done different here is told it on the boundary page, we told it to go to the boundary. So if you'll notice, the tip of the tool is now offset in by the radius of the tool. So that's where the toolpath's going. Again, just to make that clear for you, on the boundary page, actually let me double click that one. On the boundary page, it's set to, not on. On this next operation we're doing, it's set to past. So if we rewind and then play, you'll notice now the tip of the tool is going past the boundary by the radius of the tool. I would mention you can also put an extra offset of a positive or negative value to any of these selections with a value up to and including the tool radius. What this operation is showing you is when we were doing that lace cutting previously, and if I just rewind to show you again, you'll notice the step over appears to be real wide here when you're on the vertical surfaces of the part. So that probably would leave a lot more material than you would like. What this next process does, if we look at our surfaces page under advanced settings, we're telling it to do cross machining with the same step over that we did the original lace cut. So what it does is it automatically machines only the areas where, because of the contact angle of the tool, you were leaving an excess amount of material. It automatically goes in and cleans all that up for you. Next one I want to show you is radial. Radial lets you, on that advanced settings page, once you set it to radial, you can give it a center point, a starting and ending angle, and a minimum and maximum radius, and it will constrain the toolpath and direct it by those values. That's radial. Radial works really well on parts that are either completely round, or if you just need to constrain the toolpath to kind of a round area. And then this next one, we're actually going to show you two things here. This is now set to spiral with the same settings that we were using before, but instead of radial, it's set to spiral. And you can see how it spirals from the outside in. You could also do inside out if you wanted to. Okay. So that's your primary options for lace cutting. And as I said before, lace cutting is probably the most widely used finishing toolpath. In the next example, we're going to investigate in-curve flow machining. In in-curve flow, what I've done here is extracted 4 different connected profiles that actually intersect at exact points in space, and I'm going to be using that geometry to direct the toolpath. If I double click this first operation, okay, what I'm showing here is actually one of the little tricks that I use. This is actually a lace cut operation that I'm doing, but what I've done on the boundary page is told it to create for me a contact area. So if we look at just what this toolpath does, it's a lace cut. And if you'll notice, all the toolpaths kind of scrubbing back and forth. You're not going to get the exact surface finish on it because of that. But we're just using this to create a boundary of that lace cut toolpath. You'll notice now you see that boundary on a different layer, and I'm using this as in-curve flow cutting along the drive curves. So rather than it cutting back and forth, what this is doing, you can see how it's just following around that shape. And by the way, when it transitions from one cut to the next, it uses the connect move you specify, either smooth or shortest. So you'll notice here, it actually kind of arcs off of one toolpath, takes an angle, and then arcs on to the next toolpath. If you were to do that as smooth or as shortest, just want to show you the difference here. You'll notice in shortest move, it simply connects each cut with a straight line. Generally, that's not really very good on your machine tool because it's making these 90-degree changes in direction all the time. The next thing we're going to look at this is in-curve flow, but what we've done is we've selected this curve that you see in green. Go to a top view, you might see that a little better. We're taking the toolpath and flowing between this curve and this curve. Those are specified under drive curves. Sometimes that doesn't give you exactly the control you want because you'll notice it's just connecting the end of those curves with basically a straight line. So in the next example, what we've done is further selected these curves as trim curves. So now the toolpath flows not only back and forth between these, but along those trim curves as well. So let me just show you that one. Notice from a top view how it's just really nicely just went back and forth between the drive curves, but yet it trimmed it with the trim curves. Next example is curve projection. Now, curve projection can be used for a lot of different things. But as a general rule, I would say it's used most often for engraving on 3D surfaces. If we look at this first example, we're just cutting without any type of offset. So it's simply following this geometry that, by the way, was created from the Moore Park font that ships with GibbsCAM. It's a really simple font with lines and arcs, which does great for engraving. So this is the single. This is just single line font. So, but if I switch to the next one, you'll notice I'm telling it to offset 5 times with a step over of 0.002, which is going to take that single line font, but actually offset it for me to create thicker letters. And something else I'd like to point out on this particular file, if we look at a front view, you'll notice that my rapid moves are not going all the way up above the part. That's because on my entry exit page, I've turned on minimum vertical. That's a good way to keep the tool down close to the part without actually violating it. The system will automatically figure out what it needs to do to clear the part. So if you'll notice on this one, it offsets 5 times to the outside and 5 times to the inside to give us a much wider, thicker letter, even though the geometry we are using is just single line font. That's curve projection. And like I said, it can be used for other things, but primarily most users use it for engraving. Contouring. In GibbsCAM Advanced 3D Machining, contour process is similar to what others might refer to as constant Z-level finishing. If I show you this one here, we've got our parameters set with a 25,000 Z step, and we're just doing a constant step down of 25 thousandths. But I have additionally specified with hit flats, I alt-clicked this flat area as well as this flat area, so that it would make sure that even if it wasn't evenly divisible by 25 thousandths, it would take a pass at those Z levels. So let's take a look at that real quick. This is constant, this is contour cutting with a constant Z level. You'll notice by doing constant Z level, your step overs appear to be very wide here where the part's nearly flat. The next example is going to still be constant, but instead of doing, you can see these smooth step overs like we referred to earlier. In this next example, instead of doing smooth or depth first, we're going to do a helical sorting style. So what helical does, you'll notice you don't see that step over now because it's truly doing a helical move all the way around that part. Next example is instead of doing a constant Z step, we're going to do an adaptive. That's on your options page. We're going to do adaptive, and this is where you can specify minimum step downs with precision and also a maximum profile difference. I usually tell customers to set that the same as your Z step here, and you'll get pretty smooth toolpaths by doing that. So let's just rewind and play this one. And you'll notice now, by doing an adaptive Z level, it's cleaning these areas up much better. This next one I'm going to show you is exactly the same thing. And just instead of doing this smooth step down, we're going to do helical. You don't see that transition because it's a true helical move around the part. Our next example is going to be constant step over. Constant step over can be a very powerful finishing toolpath. Basically, if you select the entire part and your boundary is set to part bounding box on, this is the result you will get. It literally, it doesn't like project a toolpath. It unwraps these surfaces, creates a toolpath, and then rewraps that toolpath. Not projected, but wrapped. So you'll see no matter how flat or how vertical a wall may be, or anything in between, your step over amount in 3D space is exactly the same. What does that mean? Your surface finish would be exactly the same everywhere you've got selected. One more thing I want to show you in this file is, although I'm showing you this in constant step over, this applies to all other advanced 3D machining toolpaths. Matter of fact, pretty much all GibbsCAM toolpaths. You can set a top Z level of cut and a bottom Z level of cut. And when you do so, you're actually restricting the toolpath by Z values. Not having to slice the model or anything like that. You just restrict the toolpath by what you allow it to do in Z. So let's look at this one real quick. Notice it starts at the Z level I specified and it finishes at the Z level I specified. I didn't have to use any containment geometry or slice the solid into different Z levels. Just as in all other processes in Gibbs, you're just setting the top and bottom limits, Z limits. Next, we're going to look at flats cut. And while this is an advanced 3D machining toolpath, I've seen a lot of customers actually use this even on production parts when there's a lot of different Z values in the part. What flats cut does is if you pick the solid, it looks at the top number and the bottom number, and it creates toolpaths on any surfaces that are parallel to your coordinate system. It creates finishing toolpaths that are fully gouge protected and all that. So let's just look at, but one thing I'll point out, if you use the exact number of this, it will not do a toolpath on that surface. So let's just look at OpSim for a second. So in that case, it simply created as much flat as it could with that flat tool. But if you wanted to machine this surface as well, I just want to point out to you that you would need to set this Z value slightly below that surface. If we rewind and play this one, by setting that Z just 1,000 or so deeper, it actually cuts that flat as well. Flats cut's a really powerful tool. Now we're going to look at a couple that are pretty similar, but they're actually different. Intersections and intersections rest. Intersections is typically done with ball nose end mills. And what it does is it takes the diameter of the tool you're using, in this case, a 1/2 inch end mill, in any areas of this part that have curvature, have internal radii, where the curvature is the size of the tool or smaller, it will create what many refer to as pencil trace cutting. So we'll show you how this works. And again, you will notice we're arcing in Z and also in X and Y and making these cuts and doing all these rapid moves between parts. That's intersections. And by the way, that's just a single cut. But on this next one, I've got with offset, much like what we did with the engraving, the projection machining. I'm going to do 5 offsets, 2.5 thousandths apart. So if you rewind and show what this one does, you'll notice it does 5 offsets out and 5 offsets up from the original. And all those toolpaths are connected together in a very efficient toolpath. Next is intersections rest. While it may first appear to be very similar to intersections, it's really a lot more powerful. We use this in our machine shop quite often. Intersections rest actually looks at areas, in this case, a reference angle of 80 degrees. Anything between 80 and 90 degrees, it's actually going to do a helical down type toolpath. And in the other areas, it's simply just going to follow along. So let's look at what it does. And basically here, all you're telling it is the diameter of the previous tool, and it automatically figures out what areas it needs to machine. I dare say intersections rest is probably one of the most popular methods of cleaning out material that previous ball nose end mills couldn't get into. And you can see very clearly there that helical down motion I'm talking about. So if you, in intersections, it would just be running that tool up and down that wall. Quite often, that's when you'll break tools, especially with tiny end mills like 10 thousandths diameter end mills like we use. You don't want to be running the tool up and down in Z. That helical motion is much better. Okay, so that's intersections rest. Next thing we're going to look at is steep shallow cut. And I would dare say that most mold shops that cut very large molds, like the size of these giant TV screens or the back of a UPS truck, something like that, they use this style of toolpath for finishing. It's called steep shallow cut. And in this case, we're looking at anything between 0 to 30 degrees, we're treating as a shallow area, and anything that's steeper than that, we treat it as a steep area. So we're going to do a Z step and a step over of the same, but what you'll notice is it actually like does, you remember when we did the contour, which was like planar Z finishing? This combines that with constant step over in the flat areas. So basically you're doing Z level contouring in these areas, and you're doing constant step over in the flat areas, and it ties it all together. It makes a really nice toolpath. Calculation time on this one is a little bit longer than it is on the other. Now we're going to talk about a couple of tools that I've found to be very helpful. One is toolpath splitter. Toolpath splitter can be used for a number of things. Like for instance, let's say you're machining a part and there's an awful lot of machining to be done in it, and you know the tool just isn't going to hold up. Well, in that case, you could define multiple tools that are identical, and when you do your first machining process, in this case we're doing pocketing all the way down here, and then these other processes, all they have is toolpath splitter. So since this is pocketing, I just want to show you what it's doing. Let me rewind that. It's going to cut the first Z level with tool number 1, and then switch over to tool 2, and then tool 3, and then tool 4. The thing that's kind of amazing to me is how close the cycle times are on these. If I go to my operation manager and tell it to calculate the times, you'll notice a minute 48, a minute 46, a minute 41, and a minute 49. You might ask, well, why is that a little different? It's because toolpath splitter will always, in this case, finish one Z level with one tool before it switches to the next one. So the cycle times will vary a little bit, but as you noticed, it doesn't very much. So that's one application, is with pocketing. I have another application I want to show you for toolpath splitter. This is when we're using lace cut. And again, the first process is a lace cut, but the next ones are all just set to toolpath splitter. That's the only thing it'll let you set. Once you set it to toolpath splitter, it just says, I'm splitting the toolpath for you. And again, if you look at how this cuts, and as in pocketing it completed at Z level, when you're doing lace cutting like this, it'll make sure that it stops to change tools on the edge of the part, not over the middle of a cut. And again, if you wanted to see the toolpath differences, 439, 441, 440, and 435. Very similar to cycle times. This is also handy if you've got a machine that has a limited amount of memory. You could do this and post the code for different operations so you could break your file up automatically, not have to do that in an editor. Next example, and actually this is the last example of advanced 3D machining processes, is tool holder gouge checker. What tool holder gouge checker does is, in this particular case, this first tool, you'll see I've only got sticking out about 400 thousandths. The next tool, 800. The next tool, 1.2. And the next tool, 1.6. So what tool holder gouge checker does, similar to what we were doing with the toolpath splitter, is it's automatically moving the toolpath away from the part when it sees that the holder is going to hit. And then the subsequent processes will come in and only cut what's remaining without cutting any air. You'll notice each tool just gets closer and closer to the part. That's tool holder gouge checker. That's all of the advanced 3D machining processes. Now we're going to look at some of the surface machining processes from SolidSurfacer. First, I want to look at, on our options page, this is constant Z rough, also cutting the surfaces. So even though lace cutting is thought of as a roughing tool, as a finishing toolpath, you can do roughing with it in surface machining by just going to the options page. The next one is also a style of roughing on the options page, but it's Z surfaces offset rough with constant Z shift. This will be more easily understood if we look at a front view. You can see how it's constantly shifting the Z up. So if we look at how that actually looks on rendering, you can see how it just took the final toolpath and just kind of shifted it up. And then the third one we're going to look at, again on the options page, is Z surfaces offset rough, but with a constant number of passes. And if you look at this one from a front view, you'll notice it's not really doing it the same. Instead of shifting up constantly in Z, it's almost like it shifts it outward in X and Y. So those first three are just different ways you can use lace cutting in the SolidSurfacer toolpaths to create roughing cuts. This is a lace cut where I'm just doing a finishing, one finish pass with all surfaces. Again, that's on the option page. One finish pass, all surfaces. And for this one, I'm actually going to switch from OpSim back to ToolSim. You might notice that I switch between ToolSim and OpSim quite a bit. I also switch between those two and MachineSim quite a bit, depending on what it is I really want to see. Okay. This next one, if you remember what we were doing in Advanced 3D when we were doing the cross machining, well, this is in SolidSurfacer or surface machining. This is normal vector constraint ridge cleanup. It does the same thing that you saw in Advanced 3D. One thing I would point out as a difference is you've got a lot more rapid moves here. In Advanced 3D, it connected all the toolpaths together. It'd take a little bit longer to run this one because of the rapid moves, but at the end of the day, the resultant part would be the same. This is surface flow cut. And I want you to notice in surface flow cut that if you select a lot of surfaces that can't be done by one single selection of tangency, for instance, if I say right mouse click, select fillets, it knows that the endpoints of these fillets are the same. I can control pick another set of them. Those are the same. In other words, the endpoints of those faces match up with each other. So if I just redid that toolpath just like it is right now, it actually creates two smooth toolpaths, but I didn't cut those areas. But watch this. If I select those as well and redo it, it now breaks every one of them into individual toolpaths. Another way of doing it would be to do two curve flow. If you remember in curve flow, well, two curve flow works very much like that. I don't have the helical down option that I do in Advanced 3D, but I can still cut that part. One thing you can do here that Advanced 3D will not let you do is you can pick a point in a curve and the solid, and it will generate a toolpath between that point and that curve. We mentioned there were four major process groups: Advanced 3D machining, surface machining, which we just looked at, and the last two are Plunge Rough and Rotary Rough. In Plunge Rough, and I have people ask me all the time, well, when would you use plunge roughing? As a general rule, most machine tool guys tell me that if the cuts that you're making are at least 5 times in depth what the diameter of the tool is, it might be a good idea to plunge rough the part. So if you look at this particular process here, we're doing a linear tool path of a core. And one of the things I'd point out to you is if your tool is not center cutting, you need to use uphill as your pattern, because you can't cut downhill with a tool that's non-center cutting. And both the zigzag and one way would be downhill cutting at some point. So let's just look at what this does. Actually, I'm gonna slow this down just a little bit. This is linear. And you get to specify a step over and a step forward amount. And basically, this is like a whole bunch of drilling cycles that you're doing to rough out material. Another option I want to show you for plunge is you can do circular. And in this case, I'm specifying a radius bigger than the part. But because I shouldn't close that, because I also have use stock turned on, even though the radius I'm specifying is bigger than the part, use stock will automatically trim it to the stock size. So let's just see what this does. This is circular. And again, you'll notice I'm only doing uphill cutting. I'm not letting that tool cut in a downhill fashion, because if non-center cutting, that would be a problem. Well, that's all we have. As you can see, GibbsCAM has many different options to create efficient gouge-free toolpaths. I haven't even shown you all of them, but it's an extremely powerful package. Go back to this first file here. We are going to take some questions. Bart Ellers is going to join me, and he's been keeping an eye on the questions that's been coming in. If you have any questions now, you can just type them into the question box, and we'll do our best to answer as many of them as possible. Bart, what questions do we have?
Hey, Tony. Thanks for bringing me in, and great job on showing the different capabilities of our advanced 3D machining. As usual, you did a really good job, so thanks. We do have a few questions, so I'm going to sort through them here. We got a couple, and I'll present them to you. The first one we have is, what tool types does advanced 3D machining support?
Okay, but because advanced 3D machining toolpaths are designed specifically for cutting molds, it only supports flat bottom, bull nose tools, and ball nose tools. And it will always be gouge-free toolpaths. So those are the only three tool types that it supports: flat, bull, and ball. If you need additional support, like being able to undercut things or use other type of tools other than those three tool types, we recommend moving up to the 5-axis module.
Okay. Next one. We promote that advanced 3D machining is gouge-free, but are there instances where it will violate the part, or can we force it to violate a part, and when might we want to do that?
There's actually two cases that I can think of that advanced 3D machining would violate the part. One is if you have the surface tolerance too loose. Let me see if I can open this up to show this. On this cutting tolerance, if you have too low of a value on your cutting tolerance, it may violate the surface. For instance, if you set that cutting tolerance to 10 thousandths and you were cutting a really tiny little part, it was only maybe an inch across, chances are it's going to violate that solid because of that cutting tolerance. The only other time that I think that it would violate a solid is if you do a negative surface stock amount. But there are times when you might want to do that. For instance, if you were machining an electrode and that electrode was going to be used on an orbiting EDM machine, quite often you would want to use negative surface stock and cut the part smaller, or the electrode smaller, so that you can do that orbiting motion.
Okay. Well, I think another time that you might want to do it too, and you showed a very good example of this, is engraving, right? Oh, yeah. If you want to go ahead and force the tool to cut into the part, engraving would be a very typical application for that. So yes. What I like about GibbsCAM is we're going to keep you from violating the part, unless you specifically want to. And then we give you the control to do that. Yep. So next one. Here's a good one. Can you briefly explain the differences between SolidSurfacer and Advanced 3D?
Yes, the SolidSurfacer toolpaths are used by most of my customers when they're only cutting one or a small number of surfaces and they want to quickly get a really good toolpath that'll cut that surface in the part for them. It's just much quicker to do it with the SolidSurfacer surface machining toolpaths than it is with Advanced 3D. That's generally, and the other thing is using the surface flow cut in surface machining allows you to cut, as we saw in the example, if you have fillets that lie end to end and you want to cut those in a continual motion without having to use curve geometry or something like that, you can do it with surface flow cut, and there's no process you can do that with in the Advanced 3D machining without using geometry.
Well, to just expand on yours a little bit of background for people that aren't aware. So GibbsCAM has two 3D machining toolpath engines. The first one was called SolidSurfacer. And as Tony said, that was intended for very quick, very easy, very simple to use 3D toolpath. And it remains that way today. It's very simple to use and it generates good toolpath. Then we came out with the Advanced 3D machining toolpath that, as Tony has illustrated here, gives you far greater control, more options, and you can do far more complex cutting strategies with that advanced engine. So both engines, both 3D toolpath engines, remain in the software. And just to clarify, they aren't separate options. So when you buy our 3D machining, you get both the toolpath engines, SolidSurfacer and Advanced 3D machining. But if you just have a really simple surface you want to cut real quickly, SolidSurfacer toolpath, real quick, real easy, may cut it just fine for you.
In addition to that you just mentioned, also Rotary Rough and Plunge Rough are two other processes that come when you purchase Advanced 3D machine.
Yeah. Well, I always like to use the tagline for GibbsCAM, simply powerful. So SolidSurfacer, the original toolpath engine, is very simple to use, but then the new Advanced 3D machining toolpath is far more powerful.
Absolutely.
Yeah. Let's see, next question. How about this one? If you have GibbsCAM 2.5D solids milling, can you program any 3D surfaces with just the 2.5D solids?
You can't create actual 3D toolpaths that move up and down in Z unless you've got the SolidSurfacer Advanced 3D machining option. So if you need to do that, you should contact your reseller and see what he could do about getting you upgraded to Advanced 3D, because 2.5D solids cannot cut true 3D toolpaths.
Right, it can't generate X, Y, and Z toolpath all at the same time.
Nope.
Okay, let's see, we got a couple more here. Actually, how about someone's asking if does 3D machining require any kind of a post upgrade or modification?
As a general rule, no. If you have a post that's been running your machine doing contouring, pocketing, all the traditional GibbsCAM type of toolpaths, 2.5D toolpaths, generally I've never seen a post requirement to take advantage of all the things that Advanced 3D machining gives you.
Okay, we've got a couple more questions, but they're very similar to some questions that we've already answered and asked and answered. So I'm going to leave it there on the Q&A. Let me do one last check in the queue. Hold on for just a second. Is there a method for controller limiting blocks per second in the output code?
I'm not sure I'm not sure if I understand the question. Blocks per second.
Yeah, i.e. Haas has 1 kilobits per second processing. I think this goes to kind of the look ahead capability.
Okay. If you're specifically talking about Haas machines or Finite Controls for that matter, I would point out that, for instance, on the Haas machine, there's a G187 code that's either G187 P1, P2, or P3 that controls the smoothness of toolpath and how fast it runs on the machine. We had our Haas post modified so that we get a G187 P1 for all traditional roughing toolpaths, but we use a P2 for things like helical milling and things like that. And all 3D toolpaths and all 5-axis simultaneous toolpaths, we use a G187 P3, which is the smoothest. It may take a few minutes longer to run a program in P3, but you get a better looking part. So you can control that with a G187, and the Gibbs Post Department can make it where whatever you specify as the rules, they can make it switch back and forth based on the operation type. We've done that, and it works really, really well.
All right.
Finite has similar things. I don't remember the code right off the top of my head, but Finite Controls are able to do the same thing. And again, you can have your post modified to do that.
All right. Hey, we'll take this one. One last question, because it's actually kind of, there's 2 questions that are similar. And this last question is there any future 5-axis surfacing seminars available? And I'll take that one, Tony. We just did a 5-axis webinar back towards the end of last year. And that webinar was recorded. In order to see it, just simply visit your reseller's YouTube channel, and you should be able to see a recording of not only the 5-axis webinar that we did, which was very good, but all the other webinars that we've done as well. And that answers the follow-on question, which was, where can I find this webinar in the future? Again, it's being recorded. It'll take a couple days, but it'll be posted. Recording of this webinar will be posted to your reseller's YouTube channel. If you don't know how to get to their YouTube channel, reach out to your reseller and they'll gladly show you the way. So for any of the other questions that we didn't get to, we will, the reseller will reach out to you directly and address that question that you have. But I'm gonna go ahead, we're encroaching an hour, so I'm gonna go ahead and wrap this up now and just say thanks for everybody attending. Thanks, Tony, for doing a great job. And we look forward to seeing everybody at our next webinar.